Okay, welcome to the RL Theory Seminars, everyone. Today we have Hamish presenting, and just a quick summary of how these seminars work again for everyone. So the presentation is about 50 minutes, that's 50 minutes. During the presentation, feel free to unmute and ask any questions. If you'd like, you can ask your questions in the chat, and then I'll unmute and ask the question for you. Today, our technical co-host is Kwong, and he'll be stimulating the speaker with some questions throughout the talk. At the end of the presentation, there's going to be like a longer Q&A session. So if you have some more technical questions and stuff, you can wait till the end to maybe ask those. Other than that, we can get started with the talk. And our speaker today is Hamish. So Hamish is a postdoc at UPF Barcelona. He's interested in various topics within machine learning theory, such as packed Bayes bounds, confidence sequences, and bandits. And Hamish obtained his PhD from TU Darmstadt while working at the Bosch Center for Artificial Intelligence. And so you can go right ahead now.
Okay, thank you for the introduction and thanks for inviting me onto the seminar series. So this work is about constructing confidence sets, really, for linear bandit problems. And so this is what I was doing at the end of my PhD with my co-authors here, who were also my PhD supervisors. And as you might be able to tell from the title, we were quite heavily influenced by a certain other paper about linear bandits. Okay, so the setting is the standard stochastic linear bandit problem. We'll assume there's some reward function, such as this dashed line, which is linear in an unknown parameter vector, which I'll call theta star. And the reward function can be a non-linear function of the action if we use a non-linear feature map phi. In round T of the problem, the bandit algorithm chooses an action AT and receives a noisy reward RT, which is the value of this linear reward function plus some noise epsilon. So we focus on minimizing cumulative regret. And then the assumptions we make are, we assume that all the noise variables are sigma sub Gaussian, and we assume that theta star has bounded L2 norm. The parameter vector is unknown, the feature map is known, and we assume that we know at least upper bounds on sigma and B. And some examples are black box optimization and recommendation problems. So I'm sure, as many of you know, confidence sets and confidence bounds are a core component of many theoretically principled linear bandit algorithms. And even though the title of our paper mentions improved algorithms for stochastic linear bandits, an equally good title would be improved confidence sets for linear bandits. So let's talk about confidence sets. So in a linear bandit problem, a confidence set at, say, round T is a set that contains all thetas that could plausibly be the true parameter vector theta star, given all the data available at the end of round T. So more formally, we want a sequence of sets that satisfies the following coverage condition. And this just says that with high probability over the random draw of the actions and rewards, theta star is contained in every set, theta 1, theta 2, and so on in this sequence. And because we could trivially satisfy this by just saying theta t is all of RD, we're looking for the smallest possible sets. So the gold standard in confidence sets for linear bandits is, of course, offal, and comes from this paper by Abbasi Yadkari and co-authors. So in this paper, each confidence set is an ellipsoid centered at the regularized least squares estimate, with a radius determined using a self-normalized concentration inequality and the method of mixtures. And If we have a two-dimensional parameter vector, then one of these confidence sets might look like this blue ellipse. And as you observe more actions and rewards, ideally this ellipse will shrink around theta star. And for any confidence set, the corresponding upper confidence bound is defined as this maximum over the confidence set. And this is just the largest value that the reward function could plausibly take at some action A, given the data available at the end of round T. So if we can construct confidence sets, then we can run so-called upper confidence bound algorithms. And I'll call this general recipe LinUCB. So suppose at the start of round T, the algorithm has already chosen this sequence of actions and observed these noisy rewards. Step 1 in round T is to construct a confidence set, theta t, and the corresponding upper confidence bound. We then select the action that maximizes the upper confidence bound, and we then receive a reward and repeat these steps. So this is the setting we consider and the algorithm, and this leads me on to our work. Now, at this point, I'm supposed to say, well, this previous work is very nice, but there's this big glaring problem with it that we're going to try and fix. However, in this case, there actually isn't really anything wrong with offal. It's actually already very good. So in this work, we just want to understand whether it's possible to construct even better confidence sets to use in the LinUCB algorithm. And it turns out that it is possible. So that's the main question, and this is what's in the rest of the talk. So first, I'm going to describe our method for constructing confidence sets for linear bandits. And first, I'm going to describe the whole approach somewhat broadly, and then go through some bits of it in more detail. And since we want to use these confidence sets in LinUCB, we also need to think about how we compute and maximize the corresponding confidence bounds. So that's the next thing on the agenda. After that, I'll talk about the regret bounds that we can prove for LinUCB when we use our new confidence sets. Then I'll compare our confidence sets to the offal confidence sets and offer one explanation for why we get something a little bit better. Then after that, I'll present some experimental results. And the main purpose of these experiments is to check whether the smaller confidence sets actually make a noticeable difference to LinUCB. And then finally, I'll talk about some open questions. Okay, so before all that, I'm going to quickly establish some of the notations that I like to use. So in this talk, theta star will always be the true parameter of the linear reward function. And theta is always a candidate parameter vector. So we might be interested in checking whether some theta is inside a confidence set or not. F1, F2, and so on is always a sequence of predictions. And I'll give some examples of what this sequence could look like on the next page. And finally, I'll use HT to denote the history of the bandit problem. So HT contains all actions and rewards up to and including a T minus 1, T plus 1, but not RT plus 1. And in this talk, I'm going to be talking about lots of predictable sequences. And I say that a sequence of random variables, x1, x2, and so on, is predictable if, given the history, ht minus 1, xt is no longer random. So if you prefer, you could say that ht minus 1 contains all information about xt, or you could say that each xt is ht minus 1 measurable. So for example, the sequence of actions is predictable, the sequence of predictions is predictable, but the sequence of rewards is not predictable. So RT conditioned on HT minus 1 is still random because it depends on the noise variable epsilon t. And I like to write things in matrix vector notation, such as the following. So capital phi t is a t by d matrix, which contains, whose rows are the first t feature vectors. And then bold rt and bold epsilon t are t-dimensional vectors containing the first t rewards and the first t noise variables. And then finally, bold ft is the vector that contains the first t predictions. Okay, so I'm going to be saying many things about sequences of predictions, f1, f2, and so on, where each ft can be thought of as a prediction for the reward at time t. And each prediction ft can depend on the history ht minus 1. So what are some reasonable choices for this sequence of predictions? Well, since we know that the rewards are generated by a linear function plus some noise, we could fix some parameter vector theta and then set each ft to be equal to phi of at times theta. Or if we're using the matrix notation, we could write this as bold ft equals ft times theta. Since we can choose any predictable sequence, we could be a bit fancier and we could use an online learning algorithm to produce a sequence of predictions, f1, f2, and so on. And if you prefer, you could use a linear online learning algorithm to produce a sequence of parameter estimates, theta1, theta2, and so on, and then set ft equals phi of at times theta t. Or we could just do something boring and set ft to be 0 at every step. But presumably this wouldn't be a very good choice. Okay, so later on in the talk, we're actually going to consider distributions over sequences of predictions rather than individual sequences of predictions. So the vector ft will be a random draw from some distribution pt, which is a distribution on rt. And like ft, each distribution pt is allowed to depend on the history ht minus 1. And if we wanted to do things formally, then I think the proper way to describe what pt is would be to say that pt is a probability kernel or even a regular conditional distribution that maps histories to sets in the t-dimensional Borel sigma algebra. So I'll call PT a mixture distribution, and we'll simplify things a little bit by only considering Gaussian mixture distributions. And in this case, mu t can still be thought of as the first t predictions in some sequence, and the covariance matrix capital T can be thought of as a form of uncertainty associated with the first t predictions. And since we have a linear prediction problem, we could place a standard Gaussian distribution over theta, and then define pt as the induced distribution over the function values, phi t times a. So in this case, that's another Gaussian with mean 0 and the uncentered empirical feature vector covariance as its covariance matrix. So note that pt is allowed to depend on previous actions and also previous rewards. So pt can be considerably more exciting than this choice. Okay, so with all of that out of the way, we can now talk about confidence sets again. So the general plan for our confidence set construction is as follows. So the first thing we do is we construct a collection of non-negative random processes, mt of ft and theta. And by collection, I mean that for each sequence of predictions ft and each candidate parameter theta, mt of ft and theta is some sequence of random variables. And for a fixed ft and theta, the randomness of mt comes from the random actions and rewards. So we want to construct this collection such that if theta actually is theta star, then for any ft, mt of ft and theta star is a non-negative super-martingale. And this means that its conditional expectation satisfies this super-martingale property. And a consequence of this is that mt of theta star might look like this blue line in the plot. So it starts at 1, and on average it decreases at each step, but it never drops below 0. That's the first thing we want from MT. For any theta that isn't theta star, we want MT to blow up as the number of rounds T increases. So in this case, MT might look something like this blue line. And already you can hopefully start to see where we're going with this. If we want to test whether some theta should be in our confidence set, then we just look at MT of theta for some sequence ft and check whether MT blows up. If it does, then theta is unlikely to be theta star, and we can exclude it from the confidence set. And if MT doesn't blow up, well, then this theta could actually be theta star, so we should include it in our confidence set. Now, in order to reject thetas that aren't theta star as quickly as possible, we should choose ft to be the sequence of predictions that maximizes mt. However, as we'll see later on, the vector ft that maximizes mt is not a predictable sequence. So what can we do about this? Well, due to the particular choice of MT that we will make later on, Laplace's approximation suggests that we can approximately maximize MT with respect to FT by integration with a probability distribution. So we're happy. And this is why we consider distributions over sequences of predictions. And there's some care required to make sure that this mixture is still a super-martingale when theta is theta star, which we will get to later. So the next step is to set a threshold level that determines how large the mixture MT of theta can grow before we decide actually theta probably isn't in our confidence set. And because the mixture MT of theta is also a non-negative super-martingale, we can set a threshold with Veal's inequality. So Veal's inequality is to non-negative super-martingales what Markov's inequality is to non-negative random variables. So for some level delta between 0 and 1, Veal's inequality tells us that with probability at least 1 minus delta, the mixture MT of theta is less than 1 over delta at every time step simultaneously. And the plot below is showing this threshold level for delta is 0.1. Okay, and then the last step is just to say we define our confidence sets as follows. So at round T, we say our confidence set is the set of all thetas for which the mixture MT of theta is less than 1 over delta. And we're guaranteed that this will contain theta star with high probability for all times simultaneously. And since we assume that theta star has bounded norm, we take the intersection of this set with the set of theta stars that have bounded norm. And that's it.
Okay, can I ask a quick question here? So I remember you have to impose some marginal matching condition for PTs. Is this assumed here?
So it's not stated here, but that is correct, yes. And we'll get onto that later, yeah.
Okay, got it.
Yes. So the mixture isn't necessarily a super-martingale for any choice of PT. So yes, we do have to be a bit careful there. Okay. So we're now going to construct this collection MT. And so let's consider what we want from MT. So because we want to use Veal's inequality, then of course we need mt of theta star to be non-negative for any sequence ft. Since we're going to integrate out ft, and since we're actually going to use Gaussian mixture distributions, we want there to be a closed form expression for the mixture whenever pt is a Gaussian. And finally, we want mt of theta to be a convex function of theta, such that our confidence sets are always convex sets. And this will be important when we try and compute the corresponding upper confidence bounds. So with all this in mind, we could look for a collection of the following form. So mt is the product from k equals 1 to t of the exponential of some quadratic function of ft and phi of a times theta star. So clearly this is going to be non-negative. And if we choose the quadratic bit well, then mt will look like a Gaussian density function of ft, and we'll be able to use Gaussian integration tricks to find a closed form expression for the mixture. And also, if we choose the quadratic bit well, then we'll have a convex function of theta star. Of course, we also need mt of theta star to be a super martingale for any sequence ft. And this is true if each term in the product satisfies the following bound on its conditional expectation. So we now need to find a quadratic function such that this bound on the conditional expectation holds. So in order to do that, we can use what we know about the distribution of our data, which is that the reward noise is conditionally sigma sub-Gaussian. So for any predictable sequence, lambda 1, lambda 2, and so on, this tells us that the expected value of exponential of something predictable times epsilon t is upper bounded as follows. And because given the history ht minus 1, the right-hand side of this first inequality actually is no longer random, we can move it to the left-hand side and inside the expectation, and we now have that the expected value of exponential of something quadratic is less than or equal to 1, which is what we wanted. So we could just stop here and define mt as the product of t of these exponential quadratic terms, and then mt would be a super martingale. But before that, I have a comment and some simplifications to make. So first, at the top left, this choice of lambda t times ft minus whatever times epsilon t looks a bit arbitrary. Actually, though, this is one of the only reasonable things to put here. So first of all, we have to choose something linear in epsilon t if we want to be able to use the sub-Gaussian property. And we also, if we want to get something that's quadratic in ft and phi of at times theta star, then we also need to choose something which is linear in ft and phi of at times theta star. So actually the only free parameter left is this scaling factor lambda t. Okay, so I'm now going to simplify this a bit, but as is the way sometimes, I've actually got to make it a bit more complicated first before I can simplify it. So I claim that if you rewrite epsilon t as rt minus phi of at times theta star, and then do some algebra, then the exponential term in equation 1 can actually be rewritten as the following quantity. And if we look at the last term inside the exponential, we can think if we set lambda t to be 1 over sigma squared, then actually the final part disappears, because then lambda t minus sigma squared, lambda t squared is just 0. And in that case, we're left with this quantity. And this is simply e to the power of the difference between the squared error of phi of a times theta star and the squared error of our sequence of predictions ft. Okay, so putting everything together, or by multiplying the first t exponential of quadratic terms together, we arrive at the following choice for our collection mt. And this is just e to the power of the total squared error of the true reward function phi times theta minus the total squared error of our sequence of predictions ft. And from the previous page, we know that this is a super martingale, but intuitively this checks out because in expectation, phi times theta star is the best predictor of the rewards. So for any predictable sequence of predictions, the expected value of mt at theta star will never increase over time. So does this collection of processes mt do what we want it to do? Well, first of all, since mt, if you squint at it, is just an unnormalized Gaussian density function for ft, we can use known tricks for integrating products of Gaussians to find a closed form expression for the mixture. And since mt of theta star is the composition of the exponential function and a convex function of theta star, it has to be a convex function of theta star. And then finally, since mt of ft and theta essentially compares the squared error of theta and the squared error of our sequence of predictions ft, we can see that the expected value of mt will grow exponentially in t whenever ft predicts the rewards better than theta. So in summary, this seems like quite a nice choice for M.
Okay, sorry. So maybe it's here. So it is a sequential likelihood ratio, right?
Yes, absolutely, yes.
Yeah, and I guess you motivated it from wanting a quadratic form and kind of found a way to come up with something reasonable. But I guess one could have started from the likelihood ratio and then write it in a different way that would, so backward. Yeah. Yeah, I'm just like imagining, right? So.
Yes, yeah. Yeah, so this mt is exactly a likelihood ratio, or a Gaussian likelihood ratio. So maybe one thing to say is, in our case, we didn't start by assuming we have a Gaussian likelihood function. We just assumed we have sub-Gaussian noise.
Yeah.
And then maybe another thing to say is, if we go back to the third line here, so I kind of said we choose lambda t so that this last thing cancels and then everything's simple, so we're happy. But this isn't necessarily the best choice of lambda t. And yeah, I guess in that case, we get something else.
Right. Do you have any particular case worked out that choosing lambda t not necessarily as 1 over sigma squared would be beneficial?
So yes, although it's something I'm currently working on, so I don't know how much I can say about it just yet.
Yeah, we can postpone it after turning off the recording, or
Yes, yeah. But I guess the short answer is there's at least one other choice of lambda, which is interesting.
Thank you.
Okay. So we've chosen MT, our collection of random processes. And next, we're going to choose the mixture distributions. So the motivation for mixing in the first place is as follows. So for each theta, we want MT to be as large as possible, since in that case we can reject each theta as quickly as possible, unless it's theta star, of course. So the problem is the maximizer of our choice of MT is actually the reward vector RT, which obviously isn't a predictable sequence, so it's not a valid choice for FT. So a solution is to average over lots of sequences of predictions. And if we were integrating some other function, say e to the minus lambda g of x for some function g of a single variable, which has a minimizer at x star, then Laplace's asymptotic formula relates this integral to the maximum of e to the minus lambda g of x. So first we do a Taylor approximation inside the exponential, and then we end up with something that looks like a Gaussian density, so we can just write down the integral, which is the maximum times some constant factor. So roughly speaking, this suggests that we can perform pseudo maximization of MT with respect to the sequence FT by integration with a probability distribution. And in our case, the equivalent of gx actually is quadratic, so the second order Taylor approximation is exact. But well, regardless of the motivation, we'll see that by mixing over sequences FT, we can obtain quite nice confidence sets. So the first thing to consider is which mixture distributions are actually allowed. And so the only constraint really is that the mixture of this process MT should also be a super martingale, so that we can use Veal's inequality with the mixture. And this just means that the conditional expectation of the current value has to be less than or equal to the previous value, as in this inequality. And since at each step t, we're placing a distribution on essentially a t-dimensional vector, we actually need to select a sequence of mixture distributions. And the claim is that if each pt only depends on the history ht minus 1, and if the entire sequence p1, p2, and so on satisfies this second equation, which I'd like to call the marginal consistency property, then the mixture really is a super martingale. And it's quite easy to show that this is true. So first of all, because pt doesn't depend on anything past ht minus 1, we can swap the order of the expectations. Then we can just use the fact that MT is a super martingale for any individual sequence FT. And then finally, we can use the fact that the marginal distribution of PT over FT minus 1 is exactly PT minus 1. And then we're done. So when we're looking at Gaussian mixture distributions in particular, the conditions on P1, P2, and so on become conditions on the mean vectors and the covariance matrices, so mu and capital T. And any sequence of mean vectors and covariance matrices satisfies the two requirements as long as they obey this recursive update formula. So at each step, we append a new value to the previous mean vector, and a new row and column to the previous covariance matrix. And then each new element of the mean vector and each new row and column of the covariance matrix can depend on the history. Of course, because capital T is supposed to be a covariance matrix, it also has to be symmetric and positive semi-definite. Okay, so finally, as promised, for any Gaussian mixture distribution, the super martingale mixture has a closed form expression, which is this one at the bottom. And yeah, the derivation of this isn't that interesting, so I'm going to skip it. But if we take that previous expression, take the log of both sides and rearrange things, then we end up with this constraint for theta star. So it took a bit of time to get here, but in return, this inequality does have quite a nice interpretation. So at each step t, it says that the vector of reward function values, this phi t times theta star, lies in a sphere. And the center of the sphere is at the reward vector rt, and the squared radius of this sphere is equal to the right-hand side of this inequality. So the dominant term in the squared radius is the first term, which is the weighted squared difference between the mean vector mu and the reward vector rt. And then the covariance matrix balances the impacts of the squared difference term and the second log determinant penalty term. So in the paper, we use the following standard choice for the mixture distributions. So the mean actually is just 0, and the covariance matrix is the empirical feature covariance scaled by a factor of c. And then the inequality with this choice of mixture distribution becomes the following one. And we use RMMT squared to denote the right-hand side, which I'll call the squared radius. So on the one hand, these standard mixture distributions are good enough to give us tighter confidence sets and confidence bounds in the end. And also they allow for relatively cheap computation of the squared radius. So the formula suggests that we need to invert and take the determinant of a t by t matrix. But with this standard choice, the covariance matrix is rank D. So in the end, we can exploit this, and we only need to invert and calculate the determinant of a D by D matrix. So there are some nice properties of these standard mixture distributions. But on the other hand, setting the mean to be 0 everywhere feels a bit silly. So in the top inequality, the mean actually only appears in the squared difference term. And if we could find any mean vector that's closer to the reward vector than the 0 vector, then we'd be better off using that mean vector. And yet, despite this, it's actually surprisingly difficult to come up with mixture distributions that significantly improve upon these standard mixture distributions. Okay, and with that, we're done with all the Martingale stuff, and we can see what these confidence sets, or what confidence sets based on this inequality actually look like.
Okay, so can you give us some intuition on, like, besides being, say, I don't know, from how the expression looks like, this looks like a reasonable choice, right? This covariance matrix C times phi t transpose. Yeah. Any intuition you can provide on why that's like reasonable distribution?
Yes, so I can give you my best guess, but I don't know if this is necessarily accurate.
Okay.
So with this choice of the covariance matrix, I believe what's happening is the vector of the rewards, the little rt. I suspect that this is pointing in a direction where the capital phi times phi transpose matrix has a large eigenvalue. So then when we have this identity plus phi transpose inverse in the middle of this squared difference term, I think it's damping down the size of the reward vector quite a lot. And I think that's why having a 0 mean actually isn't so silly after all.
Yeah, and yeah, I was actually thinking that having mu t equals 0 is seemingly silly, but I think it's pretty good choice, I thought, because it imposes some stability there. It's if you trust too much into your own prediction, at the beginning it'll make wild guesses and it'll actually hurt. That's what I was thinking.
Yes, yes. And then maybe the other thing to say is, so the price we pay for, having essentially a non-zero covariance matrix to dampen down this squared difference term is this log determinant penalty. But actually later on we'll see that for this choice of the covariance matrix only grows logarithmically with t anyway. So it's probably worth it to dampen down this term, which is order t at the cost of a log t.
Thank you.
Okay. Yes, so on to the actual confidence sets now. So on the left, I've plotted the parameter space, assuming theta is a two-dimensional vector for the time being. So from the Martingale tail bound we've spent all this time on, we have the following constraint for theta star, which holds with high probability. And RMM is the same radius quantity from the previous page. So this constraint says that theta star lies within an ellipsoid, as shown in blue. And in fact, it's an ellipsoid centered at the ordinary least squares estimate, or the unregularized least squares estimate, as described below. And this blue area typically shrinks around theta star as we observe more data, but especially for small sample sizes, it isn't necessarily bounded in every direction. And the reason this happens, this happens when this phi transpose times phi matrix has some zero eigenvalues. And for example, this can happen when t is smaller than the dimension d. So to fix this, we incorporate our assumption that theta star has bounded L2 norm. And then the confidence set we get, which is convex and bounded, is the intersection shown in purple. In the spirit of doing something similar to offal, we can also construct a single ellipsoid, which is centered at the regularized least squares estimate. So this time we take a weighted sum of our previous two constraints with some positive weight alpha. By completing the square on the left-hand side, we can rewrite this as a bound on the weighted distance between theta star and the regularized least squares estimate, this theta hat alpha t. There's now a different radius quantity, RAMM t, on the right-hand side, which is defined below, but we'll come back to it later anyway, so I wouldn't worry too much about the definition for now. And if we choose a relatively small alpha, then we'll get something like the confidence set shown in green, which is a single bounded ellipsoid. And for any alpha, this is actually exactly the same as the offal confidence ellipsoid, except the radius we have here, RAMM, is actually always a bit smaller than the radius of the offal confidence ellipsoid, as we'll see later. And because we took a weighted sum of the previous two constraints, this confidence ellipsoid is always larger than our double ellipsoid confidence set. Okay, so to run LinUCB with our confidence sets, we need to be able to compute and also maximize the corresponding UCBs. So I'm now going to describe how we can do that.
I just wanted to quickly jump in. I just wanted to point out that there's like 10, maybe 15 minutes if you're able to finish in that time, maybe.
Yes,
I saw that there's quite a few more slides, so I don't know, just so like you're maybe more aware. Maybe like 15 minutes.
Yes, I think we're through the
Yep.
heavy bit, so to speak. So yeah, it should be okay. Okay, so the upper confidence bound corresponding to our double ellipsoid confidence set is the solution of this convex program. And we can visualize this problem as in the plot on the left. So the arrow represents the feature vector phi of A, and we just want to go as far along the direction or this direction as possible while remaining in the purple intersection. And the argmax is shown as theta UCB on the left. So there isn't a closed form solution, but for any action, the solution can be computed in cubic time using interior point methods, so it's still fairly cheap. And when we run lin UCB with these confidence sets, we call the method convex martingale mixture UCB, or CMM UCB for short. The upper confidence bound corresponding to our single ellipsoid confidence set is the solution of this other convex program. And once again, we want to go as far along the direction of phi A as possible until we reach the boundary of the ellipsoid in this case. So this time there is a closed form solution. And as a result, when we run lin UCB with these confidence sets or bounds, we call the method analytic martingale mixture UCB, or AMM UCB. So we've seen how we can compute the confidence bounds, but to actually run lin UCB, we also need to maximize the confidence bounds with respect to the action. And if the action set is finite and not too large, then that's pretty easy, so we're happy. But if the action set is continuous or infinite, then exact maximization is generally intractable. Although this is an issue with other linear upper confidence bound methods as well. And these figures are just showing some examples of the kinds of functions we need to maximize. So in our experiments with continuous action sets, we propose to approximately maximize the upper confidence bound with gradient-based methods. And for our double ellipsoid confidence set, or CMM UCB, we can actually compute the UCB and its gradient numerically using differentiable convex optimization methods, which is surprisingly easy to do thanks to this library CVXPy layers. So I'm now going to, yes?
Yeah, so there is this convergence, like, do we know if it will converge to a global optimum there if you use these methods?
No, it isn't guaranteed to, no. But I guess it at least sometimes seems to work okay in practice. Okay, so the regret bounds we get for lin UCB with our confidence sets. So because our double ellipsoid confidence sets are always smaller than our single ellipsoid confidence sets, any regret bound for AMM UCB will also apply to CMM UCB. So we only need to worry about the regret of AMM UCB. And since AMM UCB uses confidence ellipsoids, which are essentially the same as the offal confidence sets apart from the radius, we can reuse lots of the offal regret analysis. And the main thing we need to do is to find a bound on this different radius quantity. So this is the full expression for the AMM UCB radius quantity from before. And this is a bit of a mess, but if we choose a specific value of alpha or c, it becomes much simpler. So if we use the matrix inversion lemma, then we can see that the first quadratic term is actually the same or the opposite of the second one, except alpha is replaced by sigma squared over c. So if we just choose alpha as sigma squared over c, then these quadratic terms cancel out, and then the only thing we need to bound is this log determinant, which we can do using the determinant trace inequality from the offal paper. So we get an order d times log t bound on the squared radius. And well, in the paper, we show that you can bound this squared radius for any choice of alpha and any Gaussian mixture distribution, but it then becomes a lot messier. Okay, and then from here we can follow the standard offal analysis. So first we use the fact that actions are chosen optimistically to bound the cumulative regret by the sum of the confidence bound widths. Then, if we're running either of our two methods, we can bound the upper confidence bound minus the lower confidence bound by the analytic confidence bound minus the analytic lower confidence bound, since it's looser. And then the final step is to separately bound the radius at time capital T minus 1 and the sum of these weighted norms. And well, we know how to bound the radius now, and the sum of norms can be upper bounded using the elliptical potential lemma. So we get, after all this, a d times square root t times log t regret bound, which only matches offal. So we don't get an improved rate in our regret bounds. So we've just seen that our regret bounds only match the rate of the offal regret bound. So in what sense is our method actually better than offal? So I'm now going to compare the confidence sets, and we'll show that that our single ellipsoid confidence set is always a bit smaller. So to construct our confidence sets, we derive and use a bound on the noise vector, this bold epsilon t. And from this inequality, we can get a confidence ellipsoid centered at the regularized least squares estimate, which has the following radius. And in contrast, offal uses a bound on the weighted norm of the projection of the noise vector, which looks like this. And this leads to a very similar but slightly looser confidence ellipsoid. So in the radius of this confidence ellipsoid, the log determinant and the b squared terms appear under separate square roots. So the natural question to ask now is, why do we have everything under one square root and why doesn't offal? And the short answer is that bounds on the norms of epsilon t and theta star fit together a bit nicer or a bit better than bounds on the norms of the projection of epsilon t and theta star. So to see why, we can look at where the constraint for the offal confidence ellipsoid comes from. So we start from the weighted squared difference between theta star and the least squares estimate, using the formula for the least squares estimate and then the triangle inequality, we can rewrite the weighted squared distance and then separate the two terms inside the norm. And this leaves us with two terms that we know how to upper bound. And it's this triangle inequality step that causes the log determinant and the b squared terms to appear under separate square roots. And in contrast, we combined our two constraints by taking a weighted sum and then completing the square, which seems to introduce less looseness. So I'll now present some experimental results, and I guess the main purpose is just to check whether there is much of a difference between CMM UCB, AMM UCB, and offal in practice. So at the top, I've just plotted all three confidence bounds where the feature map consists of 20 random Fourier features. And in this case, CMM UCB is a little bit better than AMM UCB, which is a little bit better than offal. And then the plot at the bottom shows the average widths of each confidence bound. So the upper confidence bound minus the lower confidence bound. For different sample sizes on the left and different feature vector dimensions on the right. And we see the same pattern as before. And by the time we reach d equals 100 on the bottom rightmost figure, the average width of the offal confidence bound is up to about 50% larger than the width of our CMM UCB confidence bound. So there is sometimes a noticeable difference. And then we also used our variants of lid UCB and offal, as well as a couple of other linear bandit algorithms to optimize the length scales of a kernel SVM for 3 different classification data sets. In this problem, we actually do have continuous actions, so we are doing gradient-based approximate confidence bound maximization. And in the table, we record the average and maximum test set accuracy or expected reward over 500 rounds. So our variants of LinUCB and OFFL both appear to work quite well, and we see that our smaller confidence sets do improve the performance of LinUCB a bit. Okay, so finally I'm going to talk about an open question that came up with this work. So the mean vectors and the covariance matrices of the standard mixture distributions can be written in this form. So M is some fixed mean function, in this case just 0, and K is some fixed kernel function, in this case a fixed linear kernel. But the requirements on the mixture distributions actually allow us to update the mean function and the kernel function at each round using previously observed actions and rewards. So with this in mind, we also tried out mixture distributions in this form, where the mean function and covariance functions are updated in each round and are as follows. So there's two reasons for this choice of mean function MT and kernel function KT. So reason one is that the fixed mean and kernel functions can be viewed as the prior mean and covariance functions of a Gaussian process. And then MT and KT are actually the posterior mean and covariance functions of a Gaussian process. And then reason two is that for any positive definite kernel function, this choice of capital T is actually always a positive semi-definite matrix. So the question really is, when do more adaptive mixture distributions actually help us? So we ran AMM-UCB in one of the hyperparameter tuning problems from before, once with the standard mixture distributions and once with this more adaptive sequence of mixture distributions. And in this problem, it did make a small difference to the expected reward at each step. We also recorded the RAMM radius quantity with each mixture distribution. And before we bounded it by order d log t, but in this case, it actually looks like the radius is or could be bounded by a constant in t. Now, because of a recent lower bound for adaptive linear regression, it's actually not possible to remove any log t factors from the regret bound simply by having better confidence sets. So clearly this can't happen all the time. So the question really is, when do these adaptive mixture distributions actually help us? And with that, I have reached the end. So thank you all for listening.
Thank you.
Okay, yeah, I think I just, I have this. Yeah, can we look at the open question again? You had,
Yeah.
Yeah, I think maybe for adaptive, this confidence set, you could achieve like log t, where you would have condition number of the covariance matrix inside the log. So I'm thinking maybe that's what's happening here. Yeah, I don't know.
Yes, I suppose so, although... Yeah, I guess I'm not really able to give an answer.
Right. Yeah, I think so. At least in this linear model setting, the only thing we could hope for is log t instead of log t. Because you can't achieve something better, right? Due to log iterative logarithm.
Yes. Yeah.
But I'm wondering if this kind of mixture thing could benefit in other settings. Yeah, I've seen there was a paper where they talk about this benefit of doing empirical based. Have you thought about some connection of your method to empirical base?
No, not really.
Yeah, I do feel there's some connections, but yeah, I do recommend like there was some sort of a empirical based tutorial for frequentists or something like hesitant frequentists or whatever. And they have a
Oh,
very
yes.
particular example where yeah, trying to form a prior based on data helps. And yeah, I was wondering if this kind of your sort of techniques. I mean, it's clearly the empirical base would be violating your assumption there that it has to be predictable. But yeah, I do feel that yeah, I don't know, something like your thing can be applied to. There's like really nice simple example that they show where empirical base help. Yeah, I was wondering if maybe some of those adaptive, this predictive mixture could be helpful. I don't know.
Okay. Yeah, it's not something I've looked into.
Yeah, I
much.
can send you the reference.
Thanks. Yeah. Thanks for bringing this to my attention.
I think I might stop recording here.